Captain.
It wasn't you, Kevin, that was sucking. It was the rest of the class. I mean, I got one aye captain out of it. All right, last little segment that we will finish off hopefully today. If I don't get a chance to do any sort of review with you guys, we can meet up tomorrow and do a review, and we'll figure that out as the day progresses. So, all right, so we're going to talk about prop systems. So we know all about props. Before we ran off, though, Mark had a question about, hey, what kind of things would the FA ask you? And I believe it was something, was it specific about these props? Not really. There's not a lot of specific questions about props, I don't think. In our review, I will go over some of the questions. But I don't think there was anything specific. But you had to kind of understand basic propeller operation, which is really what we did well, it's not really what we did. We really did it well, I think. And I went into great depth, probably further depth than you needed to go into, but hey, there you are. And now we're going to get into the propeller. Well, I'll back up and finish that thought. One of the reasons why I go over the Hartzell and the Macaulay and the Hamilton Standard and all that is it's twofold. One, because there are questions that on your the written test that are a little bit more specific to each one of those props, but it gives you a chance to go through and look at some of the way each one operates and some of the schematics, and I help you walk through it to the point where you should be able to look at any schematic and figure it out. So that is my goal. So, all right, so we've discussed and studied propellers, and now we're going to go into some of the auxiliary systems. The FA does not get very deep into these, so we're going to go more surface knowledge on some of this stuff, not necessarily how some of the black box components work, but enough that you understand them, enough that you can inspect them and even work with them, especially on inspections. Because if you don't understand it and you're trying to inspect an aircraft, it makes no sense. And the first thing we're going to talk about is the propeller synchronizer systems. And I chose this particular photo for two reasons. A, it's cool. But B, I don't think that it was actually an accident that when the photograph was taken of this, the blades on the right side matched the blades on the left side. In other words, each blade is in the same position, or at least very close to it, not quite. And I don't think that was an accident. Rather than having one engine going right and left and the other one being it this way, they're almost matching. And that's the job of a prop synchronizer, and a synco phaser actually puts them in the same clocking position. A synchronizer helps match the engine speed. So it's going to have an engine speeds that match, and a synchro phaser, it's going to match the phase angle that each one is at. So that is what we are going to talk about next. And skip right that up. And as I had alluded to before when we first started this entire segment, is that with this particular system, when you have a multi-engine, and we're looking at something that has two engines right now, that you would have a master governor. The master governor means that's the one that says, I'm going to go this speed. And it tells the other one, the slave governor, you need to match me. So the slave governor is the one that makes the changes to match the master governor. And the way this particular system works, and it has, as you see, it says a magnetic pickup, which is to say that it has magnets that spin around and a sensor that gets an electrical impulse because of the magnet going across it each time. So it takes an electrical pulse, and that pulse then goes into an electronic control box. And based upon that, it picks up exactly what the RPMs, exact RPM of this governor based upon those electrical impulses. Then because of that, it's going to send out an impulse to an actuator, which is, this particular one is a mechanical actuator that really just actually moves the arm. And that arm is even connected into the cockpit. So you'll actually see the blue lever move a little bit in the cockpit to match what's going on here. So that'll move it back and forth. Now, these systems, especially like this older one here, they're great, but they have limitations. You cannot just start up the left engine, bring it up to max RPM, set the governor, and then flip on the synchronization switch and watch this one go all the way out. It really has a very small range of where it wants to work in. And so you got to keep it within that range. If you don't, you got to reset it and stuff. So, and inside the cockpit, so you're going to have a couple of things. One, you're going to, well, you're going to have what I'm going to show you next. And we talked about before, you're going to have this prop sync switch on off, and you're going to have this little thing right here that rotates towards the faster engine. So right now, if this were actual movie and it was holding still, I'd say, oh, they're in sync. But if they're out of sync, it's going to spin to the left if the left engine's faster, and to the right if the right engine's faster. And I think what I did, I think this is a video. I don't remember. Is it? It was. I don't even remember what all I was doing. But okay, there we go. So I'm pulling the prop handle back, and I got it out of sync. Let me go back. So what I'm going to do is I'm going to come, it's just a video I took playing with Microsoft Flight Sim. So I come up here and I'm going to pull back on the prop lever, which then means that I am slowing down the right engine, right? I'm pulling the RPM back. And so you should see over here, the RPM is going to slow down, and this indicator is going to start going, see the left engine's faster, should start spinning to the left. Then I'm going to come over here and turn on the prop sync. And when the prop sync comes on, you should see the RPM even out and this come to a stop. So let's see how close I am to being right. Let's see. There goes prop lever. It's spinning to the right over here. The prop sync came on, and now it's slowly going back to normal. Prop sync is on, it's working, now we have a matched engine speed. I don't know. I'm going to pull the left engine back, screw it all up, but the prop sync is still on, so it's going to readjust the slave engine so it's still matched again. So that's the purpose of the prop sync. Prop sync off and everything should go haywire. Hey, I do turn it off. There we go. So prop sync is off. So now it's going to match where the handles are and go out of whack. That's single phasers. All right, so we got that. Come over to here. So there we go. So prop systems, auxiliary systems. And the first one we're going to talk about is the prop synchronizer. Prop synchronizer. So a synchronizer system matches either engine speed or prop speeds as identically as possible. So a synchronizer matches either engine speed or prop speed, as identical as possible. Why? Well, this reduces noise from harmonics. This reduces noise, cabin noise from harmonics. I have a feeling with the class of this size, there's at least one person in here who every time their mom would operate the vacuum, you would hum along at nearly the same pitch, but just a little bit, and hear it resonate back and forth. Why do I feel like that would be MJ? Is MJ even here? No, he's asleep. Check him out. He's totally asleep.
I've been recording him and sending him to Janet.
Oh, that's awesome.
He pass out.
I know. There's nothing we can really do to him, is there? Like to, poke him or, let me see. Oh, we can even spotlight him. Can you spotlight video? What is that? Oh, spotlight's on there. Oh, I don't know what happened. Oh, there he is. Hey, MJ. Okay. Let's see. It is not used. It is not used for takeoff. Why not?
Because I'd be asking too much.
Be asking too much. It would really suck. It would. I was gonna add what it would suck. We'll just use the word suck. It would really suck if you were taking off and you lost your master engine, and so the slave engine goes, "Oh, we're quitting, are we?" and decides to try and match that. I don't want that. You want each engine to keep going. So that's what you want. So if I'll write that, if one engine quits, you do not want the other engine to follow. That would be asking for, that would be just a big, horrible thing. All right, so operation. Operation, one engine will be the master. Be the master, we'll say master engine. And the other is the slave. And the other is the slave engine. In a twin come with the left. The left engine is usually the master. That's because the left is the number one engine. You go from left to right. So might as well make the number one the master. The slave engine. The slave engine has the ability to adjust its RPM to match the master, within a small range. This is, I think they have newer versions that will actually a much larger range, but this is out of the book that I'm using because it seems to work. A small range, which is plus or minus 50 RPM. Plus or minus 50 RPM for a total of 100 RPM. So if it's plus 50 all the way to minus 50, that's 50 plus 50, so that's 100. Okay, so the equipment installed on each engine measures the exact RPM and sends it to a control box. RPM and sends the signal to the control box. Sends the signal to a control box. And the thing that can actually sense the RPM, it can be either the governor or you can use a tach generator. And usually on twins, you end up using tach generators because it just doesn't make sense to run a cable. Well, I'll explain that. I'll write this and I'll explain it. The sensing unit can be a tach generator, which is, it is a separate, this is a separate accessory driven item. Or a frequency generator, which is almost the same thing. Or a frequency generator. And for that one, you can use magnetic pickups. In the governor.
Which one is more common out of those two?
I don't even know which one's more common. I never really thought to pay much attention. I guess it's just how the aircraft manufacturer wants to do it. But okay, so here's the thing. On a single engine aircraft, I think a Cessna 182, 150, something like that, it's far easier to run a mechanical tach. And so what you do off the back of the engine is you actually have a cable that's spinning inside of a housing. And that spinning cable is then just run from the back of the engine to the back of, through the firewall to the back of the instrument panel. And it's a very short run, only a couple of feet. And so it's, I think, cheaper and easier to make something like that. And so that's the way a single is going to do it, or a single engine aircraft. But now take any twin, even a Skymaster, which has the engine in the front, the engine in the back, or twins like a 310 where it's on the the wing roots. It really becomes very difficult. It's a very long run. If you think about even a 310, or we go back and look at that, we wouldn't do it on this particular aircraft because it's turbines, but let's just pretend like this King Air right here has piston engines in it. To think about running a cable that is actually spinning in a housing. And when you do that, you have to either use a 90-degree drive angle adapter to make any sort of corner, or you got to make a very big loop. So if you think about the loop you'd have to make, the distance between here and here is over 6 feet. So come out of the back of the engine, make this big loop, bring it back down, run it through the loop of down through the aircraft, and another big loop and up in here. You're talking about 20 some feet of cable that's got to spin to get up there, and is prone to kinking, and it's got to be lubricated. And so you never do that. So the way to do it is you put a tach generator back there, or the magnetic pickups. Now a tach generator is basically just a little tiny generator that bolts on the back of the engine, and it's just run off the accessory drive gears. And you can do it a couple different ways. One, it can actually measure the frequency that it's actually spinning, and just run just 2 little wires off there and say, okay, well, so if it spins at this speed, you're going to get this voltage, and then just put a RPM gauge that basically is a voltmeter that's calibrated to read RPM, and there you go. So generate some volts, put a voltmeter, call it a tach, you're done. Or you can use another one that it changes by use an AC generator that does frequency, and just make your RPM gauge read frequency, calibrated to read RPM. So that's what I'm saying. So usually that stuff's already built into the aircraft. So you can pick it up off of there and then run it to the control box. So I guess I tell you that to say, when you're working on these aircraft, don't look for what you would expect to find on a Cessna 150, some sort of mechanical cable going somewhere. Look for a small tach generator that's about the size of, I don't know, they're just small round things. We have a tach generator on our ground power unit that you guys are going to be using, hanging right out in the open. So if you ask me, I'll say, oh, there's a tach generator. So they're not real big.
Hey, Kevin.
Yeah.
Are these control boxes like just electric, or is like a ECU?
No,
computer?
they're electric. I've never opened them. We don't mess with them. Never had one really go bad either. I'm sure they do, but it doesn't mean I had to deal with it. So let me see. So sensing unit. Okay, so you have the equipment. So you have a sensing unit, and then we'll have. Let me see. Then the comparison unit. So you have something that's going to tell the box how fast the engine's going, and then you're going to get to the comparison unit, which is the kind of the black box of thing that it receives the signal. REC receives the signal from the sensing unit, from the sensing. And for those of you that had electricity, this frequency generator, the magnetic pickup generator, that's what we're using on our magneto RPM gauge for the magneto test bench. It's just a magnet that comes around and hits a little sensing unit that figures out when the magnet comes around. So receives the signal from the sensing unit. Let me see. Either the voltage from the tach generator, or the frequency from a frequency generator, and then the comparison unit will adjust the slave engine to match the master, MATC, match the master, which also has to have the same stuff, the tach generator, magnetic pickup, something. So it, I think some of the newer ones are done electronically, but I think the older ones may be done with control linkage, control linkage that is parallel to the cockpit control, that is parallel to cockpit control. And by parallel, I mean the actual cockpit control is attached to the same, literally the same bolt that the control unit from the comparison unit goes to. So when the comparison unit sends a signal to move the lever on the governor, you're actually going to see the blue knob move slowly back and forth inside of the cockpit. Now, of course, like I said, you get into something like a King Air or something that's a lot more electronically controlled, then you can send stuff over to the fuel control unit. You can change everything that way. You don't have to do it in such an old-timey way. Then we have the indicator. Not all, but most twins have an indicator wheel. Have an indicator wheel that show an out of sync condition, condition. And the more I think about it, the more I wish I had one of those for my life. And whenever it starts spinning to the left, I can know my wife's kind of pissed off at me. And if it's spinning to the right, I know she's kind of happy with me. So she didn't watch these videos, so I'm okay. Yeah.
So when you turn on the synchronizer, are the levers disconnect at that point?
No. Nope.
Do they move then?
Yeah. Yeah. In the system I'm showing you, they'll move.
Oh, okay.
They'll move. The indicator will rotate. Indicator will rotate toward the faster engine. If the engines are in sync, the indicator is stationary. Thanks, Eric. All right, so in addition to the synchronizer, excuse me, synchronizer. So let me see if I can, before I move on. If you can make heads or tails of this photo, this is the arm right here that is connected to the cockpit control. And in this case, they don't actually show the cockpit control. I could do it. I could say there's a rod going from here that goes off to the cockpit control. You can see that this shaft comes in and it's connected right to that same arm. Then it's going to move the arm back and forth. And this arm is connected into the control cable in the cockpit. So if this bar moves back and forth, it has to move the blue control back and forth because it's actually connected to that. So that's it. This is shown top view here, and that's the arm right there that you're looking at. Synchronizer, we don't use the synchronizer on takeoff because it's really bad. Okay, the next thing we have to look at is the syncophaser. Sounds cool. Phaser. Sets the propellers of the aircraft at the same angle. So this particular aircraft we're looking at represents a Cessna Skymaster, where you have one engine in the, I think this is the front here. Yeah, the front's lower, so that must be the front, just an ugly looking picture. And then in the back, you can see that's the rear propeller. So in this one, the phase angle for each one of them is 0. And this prop is up, this prop is up. Or you can get it out of phase by 20. So when this one's up, this is off by 20 degrees. And of course, this one's off by 48 degrees. And so as it says here, syncophasing sets the propellers of the aircraft at different angles and keeps them at the same RPM. So not only does it work as a synchronizer, but then it will actually set where it is in relation to the other propeller. And this is just taking it one step further than a synchronizer, which is trying to pull out harmonics and such. But this one puts it in the same or different phase angle. And the reason why you would want to do that, again, especially in this particular aircraft where you have a pulse from the prop going over the aircraft, I think you want that pulse to hit this. You don't want the pulse to hit the prop. You want the prop to get more of its own fresh air, which I don't know, seems kind of a weird concept because there were a lot of planes built, and even boats do it now, where you have counter rotating props, one right behind the other. And anyway, I'm getting off on something. So let's see. So syncophaser, I think that's the only thing I have for syncophaser. Yes, it is. So syncophaser, not a whole lot to say about it, but two. Propeller, prop, syncophaser, S-Y-N. C-H-R-O, synchrophaser. Synchrophaser. So we'll just say incorporates the features of a synchronizer. Features of a synchronizer. But adds propeller, adds prop phase adjustment. What is phasing? Phasing is the relative position, position of the prop blades, So the phaser, it sounds a lot cooler than it really is. If I say, well, my plane has a phaser on it, you think, no kidding, that sounds awesome. The phaser sets the number of degrees, the slave engine is, let's see, phaser sets the number of degrees slave engine is, we'll say, past, oh, I know a better word. Number of degrees a slave engine lags the master engine. I want to say lags, or I want to say leads. I guess it's a relative term.
Slaves don't lead masters.
Oh, I'm not going there. Leads. I don't know. It should. Is it lags or leads? Let's see. So I'm changing my wording around so it sounds better. So this one is 20. So let me think. Which way is the prop going to rotate on here? So normal rotation is right. So to me, it's going to be left. So that is behind. Except, let me think. This is going to be tricky here. Thinking on the fly. Pin. Okay, so the front engine, if we're looking at the front of the aircraft, which we are because that is lower, the front engine sits lower on a Skymaster. So we're sending the front of it. And proper rotation would be this way for the front engine. And if I'm looking at it, then now I am at the pilot's perspective of the engine, because the engine is backwards in the Skymaster, and because it's backwards, it is a right hand, so it's actually going this way. So I don't really know if I should have opened that can of worms, or if they even intended me to think this one through. So I don't know if it's either leads or lags. It's just different. Different works. So you guys follow my chain of logic there?
Yeah. Well, it is behind, so it will lag.
So in my original notes, I was probably smart enough, and I should have changed it. I said the phaser sets the number of degrees a slave engine is past the master, but engine leads, lags the master. Just, you can put leads and lags. There you go, and then we figure it out. Because not all of them are twins like that. And let's see, cut some of this out. Uses a pulse generator. Yeah, what the heck? Uses a pulse generator. Keyed to the same blade, to the same, what the same? Keyed to, I'm going to make it more simplistic. Keyed to one blade of each engine. One blade of each engine. And you're going to set up one of these, either pulse generator or electronic eye. You guys will do that when you get into prop balancing. And so you put a little piece of reflective tape on a spot on the one blade, and then you have an electronic eye that actually will sense where that blade is coming around. So that's another way to do it. So pulse generator key to one blade of each engine. So the pulse generator gives RPM, and position information. So obviously, if the pulses are the same, the blades are in sync. If the pulses are different times, but at the same frequency, then it's out of sync, but at the same RPM. The control unit will adjust the governor as needed to keep engine speeds matched and at the correct phase. And how do you set that? I think there was a picture. No picture. Well, I suck. There's a control. I don't know why I don't have it. A picture control box. Oops. Oh, screwed up now. I want this picture. So there's a cockpit control. A cockpit control. Control allows the pilot to vary or to change the phase angle to reduce noise. I was looking at the MJ notes picture and I didn't see MJ. I'm thinking, dude, that dude, he just went to bed. But I see you're up there in the top, upper left.
I did doze off a little bit. That video though.
Yes,
Like,
we noticed.
and then I just hear my name like, oh my God, he's writing notes.
Okay. Next thing, Otto Feather.
Can you go back to the notes real quick? I'm gonna take a picture of it. Just move back. Thanks. All right, you're good. Thank you.
Okay. All right, Otto Feather. So Otto Feather is something that, well, it does exactly what the name sounds like, and it will automatically feather the engines. And the reason why that is something that you might like is that during takeoff, it's a pretty high pilot workload, and I don't, full disclaimer, I don't have a multi-engine rating, but I will tell you this, that I've been told one of the most common problems with flying a twin engine is misdiagnosis of engine failure. And to give you an example how easy this is, I know about it. I know that pilots often will often shut down the wrong engine. You know, you've just lost half your power. Things are going to hell in a handbasket. You're under tremendous amount of stress. You know you've got to shut down and feather an engine, and they do the wrong one. And so you had one working engine and you just put it away and left your engine that was dragging you down running. And so that does happen. And knowing about this, when I went to school for citations, it was really cool because we got to use the citation simulators, full access simulators. And these simulators are it. It is amazing. In class, we talked about interlocks between some sort of thing, and I don't even remember what it is anymore, but the instructor saying, oh yeah, if you're in the citation, you can reach up and you can feel this thing and you can do it. We get into the simulators. He goes, oh yeah, I was talking about this. He goes, reach up, you can feel it. It's in the simulators. I mean, it is everything out of a citation is right there. It is real. They use so that it's not simulated at all when you're in that cockpit. And so as a mechanic, it was awesome. And so what we would do in the simulators is we would go in and we would, they run off an auto start sequence. And so you just hit the start button and lights go on all over the place. And they happen really fast. Like, you'll start, the ignition sequence, and then the starter sequence and the fuel sequence. And there's all these different things that happen. I forget, it was about 7 or 8 things. And what we had to do is be able to take our finger and hit the light that was going to come on at the time that it did it. So you knew exactly what was going on. It could follow through this whole sequence for troubleshooting the starting of the citations. So that was one of the things we did. It was really cool. But so another thing we did, we had to go through emergency procedures, what to do in case of fire, how to rock the fire bottles and all that stuff. So I'm like the second or third guy that was going to do it. And I'll be honest, I was well prepared. I knew what I was going to do. But being the third guy in line is always helpful because you can watch other guys make mistakes. And so, these guys, they fumbled through it. They couldn't get the engine shut down. They couldn't get the fire bottle set off. I mean, it just blah. So it's my turn. And I'm like, dude, I'm going to nail this. And I hit the start sequence, every button perfectly. We got it running. He initiated a fire. I ran through the whole sequence, textbook to perfection. And I was so proud of myself. I look over the guy and I smiled. He goes, Kevin, that was awesome. Too bad you just shut down and put the fire out on the one good engine we had. So I'm like, what? Ouch. So even under a simulation, even knowing what he was going to do, the stress involved, I shut down with nothing at stake. I mean, absolutely zero at stake. I mean, the guys that screwed it up before me, it's not like they failed the class. We just kind of laughed at them a little bit. Yeah, screwed up. And they did it again and got it right. So zero at stake, and I still did it. And so that instilled in me this absolute appreciation for a pilot and the workload trying to shut down the correct engine. And so anyway, so I'm told that that's one of the biggest problems. So this Otto Feather sort of takes the guesswork out of it. And so an Otto Feather will automatically shut down and feather an engine that loses power all on its own, so the pilot doesn't have to guess which one was bad. So, but it is usually typically used for takeoff and landing only. And the reason why is because if you're flying along at altitude and you have some sort of hiccup, burp, fart out of your engine, you don't want it to go into the shutdown because it could have just been, a little gas bubble in the fuel line system or some weird anomaly. And so you don't want it to shut down and go away. You want to just see if the engine's going to go through its process and keep working just fine. So, so once you're up at altitude, you shut it off, and you're only going to use it for the emergencies when takeoff or landing. So when armed, system is activated. System is activated with power levers over 50%. So in other words, you can arm the system, but it's not going to activate the system until you get over 50% power on the aircraft. So if you're just down there and idle, it knows that you're not flying. So why arm it? Why go through this process? So it causes the prop to feather if torque pressure switch senses a drop below a preset limit. Torque pressure switch senses a drop below a preset limit. That reminds me, I had a client, he's the same one that had a twin Baron, the same one that had the reversing props on it. He had thrust indicators on his aircraft, and what they were like little pitot sensors on the bottom of right and left cowling that were just right behind the prop. And so it would sense the prop wash. And if there was a variance in the prop wash between either one, then it would set off an alarm and point to the whichever engine had lost its thrust.
Hey, Kevin.
Yeah.
This is a little off topic, but if you lose an engine in a twin engine, are you like heavy on one rudder pedal, or are you adjusting the rudder trim to like compensate for that one engine being down?
God, Phil would be the guy to talk to about this because he's fully rated in twins. So yes, my understanding, and having never done it, is you are hard on that rudder. I mean, it is like all rudder at that point, especially if you've got it out on the wings. And not only that, you have what's called a critical engine out. And because of the rotation of the props, if you lose, Harry, do you know which one it is? Is it the right or the left?
No, I don't. The only thing I've ever heard is like the little thing about dead foot, dead engine going with the rudders.
Okay, but
I thought Phil said it was the right.
Oh, he's the right. Okay, there's a blue arc on your instrument panel that has to do with critical engine out. You have to be above this airspeed. If you don't, the thing's just going to roll on its back. And so, yeah, it's you get into a twin. I never got into that because as a mechanic, I never flow them. I just work them on the ground. So yeah, but your foot's going to get very tired, and you're going to want to have rudder trim all the way in. So see, a time delay will prevent a feather if there is just a momentary power loss. If there is just a momentary power loss. Nice thing about this too, if one engine is feathered, the system will not auto feather the remaining engine. And I think that's a nice feature to have. And that brings me right to 520. So I will see you guys in just a little bit.